Now we're going to look at what happens when we have reactions that take place in solution. You may not actually have thought about it, but in the last chapter, chapter 3, we mainly talked about solids, liquids, or gases that were reacting. But typically in chemistry, what we really are dealing with is things that are dissolved and form solutions, which is partially the reason that we went ahead and talked some about molarity in the last chapter. So we're going to consider reactions of aqueous solutions, and there are three primary types that we're interested in. The first is called a precipitation, which we've already seen, talked about a little bit. The second is an acid-base reaction, which we haven't talked about. And the third is an oxidation-reduction reaction, which we have looked at, but we didn't really talk about the fact that it was oxidation-reduction or describe that. So to begin with, we'll take a look again at what happens when we have a solid that is dissolved in water. In this example, we're looking at sodium chloride dissolving in water. This is the conductivity device that we talked about earlier. And then here is what we're looking at on the molecular level. So the positive side of the water molecule, the side with hydrogen, is attracting the chloride ion, pulling it away. And the negative side of water, the oxygen side, is pulling away the sodium ions. And that's really the process of dissolving. And that's one that you should know about. This is a diagram from your book, which really is just going over the same thing that we saw in the animation, which is basically what happens when something dissolves. So to begin with, we're talking about ionic substances. So we are talking about, in this case, the potassium ion, which has lost an electron, and the chloride ion, which has gained an electron. And remember that these are attracted to each other because of the difference in charge. That's what's holding them together. Now, if you put solid potassium chloride in water, then if the attraction here between the oxygen and the potassium ion is greater than the attraction between the potassium ion and the chloride ion, and then the same thing being true on the other side, that the attraction here between the hydrogen and the chloride ion versus the chloride ion and the potassium ion. At any rate, if those attractions are greater, then a substance dissolves. On the other hand, if this attraction is greater, then the substance is insoluble, in other words, doesn't dissolve. And I also should mention that these little symbols up here, this one, this one, this one, those are used to represent charge. So that's just letting you know that this side of the water molecule over here has a positive charge, and this side has a negative charge. And we'll talk more about why that's true later. As you can imagine, it would be nice to be able to predict whether or not something will be soluble or insoluble in water, and we have some rules which are summarized in this little table, which helps us to do that. So you don't have to memorize the rules, but you do need to be able to use the table in order to predict whether or not something will be soluble. So if we look at it, we can talk about it some. So if you look sort of across here, everything with a group 1 cation or the ammonium ion is soluble, and everything with nitrate is soluble. So for example, sodium phosphate would be soluble because it's a group 1 cation, or ammonium carbonate would be soluble. On the other hand, copper nitrate, because it's in the column with nitrate, would be soluble, and all the other nitrates are soluble. Then we come to situations where things are mixed. So let's just take a look at chlorides, for example. In general, the chlorides tend to be pretty soluble. However, there are 3 chlorides that are not soluble: silver chloride, and lead 2 chloride, and mercury 1 chloride. Okay, and there's a note down here. We don't really deal so much with the bromides and the iodides, but they follow the same rule as the chlorides. And then if you have something with a group 2 cation, so remember that's magnesium and barium, strontium, so forth, then most of the group 2 sulfates would be soluble, so strontium sulfate would be soluble. But if you go over to, like the group 2 carbonate, so barium carbonate would be insoluble, that would be in here. Magnesium phosphate would be insoluble. So we'll go through and practice using this table, and I'll put it on the other slide so you can see how we use it. And one more time, you'll be given this on tests and quizzes, so you don't have to memorize the table. So this little diagram summarizes some of the things we talked about in Chapter 3. So if we look at a reaction, let's say we look at the reaction of silver nitrate with sodium chloride, and we want to predict what would happen, if anything. So the only real possibilities here would be the silver could take the place of the sodium, and the sodium could take the place of the silver. I should probably also say that I'm leaving out the aqueous, so which is unfortunately probably done more often than not, but just have to remember that in this chapter we're always talking about aqueous solutions. So on the other side we would have AgCl, and we would also have NaNO3. So all that means is we've just swapped the positive ions, the cations. Here's an example where we can predict what the reaction will look like when we mix sodium carbonate and calcium chloride. So if we start down here, sodium carbonate looks like that, and calcium chloride, CaCl2. And then on the other side, we're going to have the sodium go there, the calcium will go there. Remember that we write the formulas based on charges, not based on what they are originally in terms of the subscripts. So on this side, we're going to have calcium combined with carbonate. Remember that calcium is in the second column, and so it's +2, and carbonate has a charge of -2. And then we're going to have NaCl. If we balance this one, we've got 2 sodiums on the left. We can put a 2 here, and that pretty much takes care of everything. We can go back through just for the sake of completeness, and we can put down that this is aqueous. The rule would be that, well, it wouldn't be in a solution if it weren't soluble, but everything with a group 1 is soluble. And over here with calcium chloride, it's also aqueous. If you look at the rule, the group 2 cations, which includes calcium, is soluble with chlorides. Okay. Then on the other side, we've got 2 compounds to consider. So the first we'll look at is calcium carbonate. So if you look at the chart, you see that calcium carbonate, so we would come across here, and there's carbonate going down, and calcium carbonate is insoluble. So I'll put an S to denote that it's an insoluble substance, and I'm sure that you know that sodium chloride is soluble. Okay, and if you look over here at the picture, you can see that over here, that would be the white calcium carbonate that would form if you mix these 2 together. On this one, I went ahead and wrote out the equation just so we could save a little bit of time, and so now we have a solution of copper nitrate mixed with a solution of ammonium sulfate. So what happens? Well, let's take a look. So over on this side, we have ammonium nitrate. Is it soluble or insoluble? Well, all nitrates are soluble, so I can put an AQ there. And copper sulfate, what's going on with that? So if I look up here, I see that all the sulfates with transition metals are soluble except for lead and silver, so there would be an AQ there. So you say, well, what happens? And the answer is nothing. If we mix these together, we just have a mixture. So in our mixture we have copper ions, we have nitrate ions, we have ammonium ions, we have sulfate ions, but nothing actually changes. So this is considered no reaction. So why don't you pause the video and see if you can go through the next example and then take a look and see what I've done, and we'll talk about it. Well, I hope you got something like this. So we went through the double replacement process, we balanced the equation, and then we checked the solubility rules. So you probably are starting to recognize that anything with nitrate is soluble. And you will probably remember that silver chloride is insoluble, and if you check the list up here, you can see that right in that little box you've got AgCl. So we do get a reaction and we get a precipitate, which is silver chloride. Now we're going to take this idea of precipitation reactions one step forward, and we're going to write what is referred to as a net ionic equation. So the word net in this case means what's left over. So if you have a job and you work, you get a certain amount of money, and after you have paid your taxes, etc., what's left over is your net pay. So this is a net ionic equation, so we're going to write down just what happens in the reaction. If something doesn't happen, if something doesn't react or form an insoluble substance, then we're going to leave it out. So I'll go through this one in a fair amount of detail, and then I'll let you try the next two. Okay, so first thing is we need to write the balanced equation for the first one. So we'll do NaOH and copper 2 nitrate, and on the other side, so I'm assuming that the copper maintains the same charge. You probably remember that copper can have charges of 1 or 2, but in these reactions you assume that any ion with multiple charges keeps the same charge that it had to begin with. And then I also have sodium nitrate. Okay, so let's look at this one and figure out what's soluble and what's insoluble. So obviously soluble. You're not really dealing with any situations yet where you are given something to react that's insoluble. That's certainly possible, but that's not where we're at yet. On this side, we have copper hydroxide. And if we look, so this is the category that we'd be looking at because copper is a transition metal. And if we look over to the box for hydroxides, we see that copper hydroxide is insoluble. So what that means is that we're going to have an S there, and then for the sodium nitrate, all nitrates are soluble, so that would be an AQ. Alright, now I'm going to rewrite the equation, and I'm going to write everything in the form that it exists in the solution. And what I mean by that is this, that if sodium is an ion in the solution, I'm going to write it as an ion. I'm not going to put the AQ because I'm running out of room here. Oh, I guess I should probably say that I will balance this equation. So we had 2 here and 2 here. Alright, so that means we have 2. Oops, 2. Alright, so then we have 2OH minus, and then we have copper 2 plus 2 nitrate ions. The copper hydroxide is insoluble. Because it's insoluble, I'm going to write it together as an insoluble substance. And then finally, I'm going to write over here, I have 2 sodium ions and 2 nitrate ions. Okay, so some things changed, reacted, and several things didn't. So let's go through and mark what reacted and what didn't react. So I'm going to put a box around everything that didn't change. So I have sodium ions on the left, and I have sodium ions on the right, so they didn't change. I have nitrate ions on the left, and I have nitrate ions on the right, so they didn't change. So effectively, the only thing that happened was copper ions reacted with hydroxide ions to give copper 2 hydroxide. So I'm going to write this right up here, what actually happened. I'm going to write it completely. So Cu2 plus aqueous plus 2OH minus aqueous gives CuOH taken twice, and that's a solid. And this is referred to as a net ionic equation. So here's our first goal for this section. Given the solubility rules here, and given any reaction that is going to be a double replacement reaction, to take that information, figure out what's insoluble, and write the net ionic equation. So I suggest that you do that for the next two reactions. Stop the video and then check the answer, which I will give you, and see how you've done. Okay, I hope that you were able to get these, but let me just go through briefly and explain why these are the net ionic equations. So the first one, the barium hydroxide and the magnesium sulfate, is a little bit different than the ones we looked at before, because on the right side we end up with two insoluble substances. So verify using the solubility rules that you can identify those as insoluble. So everything is included in the equation and you can't cancel anything out. So let me emphasize that point. Something to be able to cancel something out, you've got to have it exactly the same on both sides. So just because I have barium here combined with sulfate, I can't cancel out that barium. It has to be barium ion and barium ion. In the next example, when I check and I look at the solubility of the product, so I would be looking at ammonium and carbonate and potassium and phosphate, well, everything with potassium is soluble and everything with ammonium is soluble, so nothing happens. So we just refer to that as no reaction. So at this point you should be able to complete some of the first OWL exercises, so give those a try. Be careful because they are very picky as far as all of the symbols, but it's good practice for you.